What is the Sun made of? If you have some knowledge of physics or astronomy, you will answer that the primary constituents are hydrogen and helium, and you're absolutely right. But did you know that you can find traces of all the other elements of the periodic table there as well? I'm Chris from Labtastic, and in this episode I will show you that there's sodium on the Sun. Let's start with a flame test of sodium chloride, commonly known as kitchen salt. This is a straightforward yet fascinating experiment that you may have encountered in school. By placing a few salt crystals into the flame of a Bunsen burner, a remarkable color change occurs. Whoa, whoa, whoa! Where does this intense yellow light come from? You guessed it right, that's the sodium. A neutral sodium atom has 11 electrons, with the 11th electron sitting in the third shell all alone. That electron can be lifted up into a higher state, the so-called 3p state, by the energy of the flame. What we then have is an excited atom. When the electron eventually falls back into its original 3s state, the excess energy gets released in the form of a photon with a wavelength of 589 nanometers. That's right in the orange to yellow regime of visual light. And that's why the flame in the previous experiment turned yellow. I'd like to verify this mentioned wavelength with our next experiment. For convenience, I'll use a sodium lamp instead of a flame as a light source. Those sodium lamps are extremely energy efficient and were widely used for street lighting before the dawn of LED lights. I'll use a transmission grating like this one to split up the light coming from our sodium lamp. So get ready to write down some numbers, namely the distance between the grating and the screen, and the distance between the central maximum and the maximum of first order. Because with these values you will be able to calculate the wavelength. I'll show you how it's done, however, feel free to skip that part and have the fun all to yourself. Let us now give a closer look at the spectrum by using a professional spectrograph. This is DADOS from Bada Planetarium. It's a slit spectrograph that uses a reflection grating instead of a transmission grating. A reflection grating is something like a tiny piece of CD or DVD. Let me show you. First we analyzed the light coming from a classic incandescent light bulb. Then we switched to our sodium lamp. I'm curious to see the difference. That was really insightful. While the incandescent light bulb gives us a continuous spectrum encompassing all the colors of the rainbow, the sodium lamp almost exclusively emits the specific yellow color. And have you noticed? I'm sure you have. The sodium emission line is actually made up of two separate but close emission lines, a so-called doublet. That's because this upper 3p state mentioned earlier splits up into two states. The two wavelengths are 589 and 589.6 nanometers respectively. Now let's turn our attention to the Sun. As promised, I want to give evidence for the presence of sodium there. Let's again use our spectrograph to analyze the incoming light. For this purpose, it is not necessary to point it directly to the Sun. The daylight surrounding us is merely reflected sunlight. So we can as well just point the spectrograph out of the window and up into the sky. At the first glance, that looked very much like the spectrum of an incandescent light bulb. And that's not far from truth. The Sun mainly radiates light out into space because of its high temperature. just like the glowing filament of an incandescent light bulb does. However, there were subtle differences Joseph von Fraunhofer noticed in 1814. These dark lines you saw are called absorption lines or Fraunhofer lines. Their presence indicates that the sun is not sending us all the colors of the rainbow, but is for some reason leaving some specific colors out. Fraunhofer was very scrupulous at mapping those lines and assigned letters to the most prominent ones. Ready for the highlight of the video? Hold on to your seats. We have seen that the Sun exhibits two striking absorption lines in the yellow part of its spectrum, and the light coming from our sodium lamp fits right in there. What a remarkable coincidence this is! Except for it is not a coincidence. We come to the conclusion that somehow sodium is responsible for the appearance of the two absorption lines. And moreover, we deduce that all the other absorption features present in the Sun's spectrum can be attributed to some element. So the Fraunhofer lines are actually the key to deciphering the chemical composition of the Sun, and of all the other stars for that matter. So there is sodium on the Sun, and spectroscopy is a really powerful tool. That's it. Hope you liked it.